Just to give you a quick presentation overview, high performance coatings challenge, coating selection parameters, medical electronics high performance coatings, production considerations, narrowing the choice, conformal coating comparisons, conformal coating implementation. What we're going to try to do here today is not really sell anybody on on any type of coating, but to kind of give you an educational quick overview of what you really need to be taking a look at. The coating challenge. As we know, coating can be critical to the proper functioning of a medical device. I think everyone basically knows that. Coating selection is a complex process, and a material must often satisfy multiple requirements. Medical device manufacturers must select from a wide range of coating materials and process options to effectively meet performance requirements and industry standards. Coating selection parameters. Couple things that we need to look at. I think I missed a slide, so let me just go back a little bit. Now, the key functions of conformal coatings are insulation reinforcement, moisture abrasion, chemical and UV resistance, modify surface characteristics, and also improve lubricity. Those are basically the coating selection parameters at this point. And some of the other ones would be key issues are end-use performance, obviously material process cost, environmental considerations, production efficiencies, and manufacturing integration. Some of the other ones are support tissue growth, temperature stability, flex and elongation resistance, as well as resist a corrosive environment. As we all know, there's a lot of, out in the medical device industry, and a lot of the applications now are coming under a lot of corrosive, cleaning, all different types of chemical type of processes that can affect the actual high-performance conformal coatings. There are a number of, in the conformal coating or high-performance side of things, there's a number of various coatings out there. The liquid coatings are solvents, solvent-free or 100% solves are epoxies, acrylics, silicones, urethanes, and a non-liquid coating is Parylene or polyparaxylenes. And looking at narrowing the choice, this is some of our experiences with the materials up here, but what we have done is we've actually listed the properties, the various coatings. You got Parylene, acrylic, urethane, epoxy, and silicones, the ratings. So basically, if you come down here, you can look at the flexibility, the physical strength, the low stress. So you can really get a good idea here when you're looking at a material for your device, exactly what some of these will help fit for some of these properties. So now this is kind of a good tool for you to narrow the choice down to what you really need for your application. I'd like to give you a quick overview on some of the liquid coatings, epoxies. They're durable, high-strength coatings. They have good mechanical, dielectric, and barrier properties. Solvent-free UV cure epoxies may be most appropriate to medical applications. Relatively high mass in nature with cure forces. So this is trying to give you an idea of some of the various coatings, liquid coatings, and some of the points that you can take a look at that help you in your determination of what you'd like to use. The acrylics. Commonly solvent, they're normally solvent-based, provide general electrical and moisture protection and modest physical isolation, and they're removable for substrate repair. So they're easy to remove. So there's a consideration you might want to take a look at, and it depends again on your application. Urethanes. The relatively durable composition, offer useful mechanical, dielectric, and barrier properties, and they're available in a wide range of viscosities and cure options. So in this case here, you have to take a look at really what your application is. You might need a thicker, a thicker material, so you definitely have that option with the urethanes. And it just depends really, again, on what your application might be. The silicones. Silicones are pretty well known here in the medical device industry. And why is because they're flexible, they resist vibration, offer modest physical isolation, general moisture, electrical, and chemical isolation, and removable if necessary to allow for repair. So the silicones, obviously you can remove them quite easily. One other thing is, they certainly, they do like a little bit of moisture, so that's something you have to take into consideration, but certainly silicones are widely used in the medical device industry. A non-liquid coating material is Parylene, and certainly I'm sure a number of you know about this material, but it's formed by a chemical vapor deposition, and it's really put down in a very thin film having little mass. So that's one of the big advantages of it. It exhibits no cure forces, so the fact is your parts don't see any stress during the process. It's pinhole-free forms with the equal thickness on all surfaces. So for example, if you have a needle, it's going to coat the same on the needle as down the edges, so it conforms to the actual substrate of the product you're going to coat. It also accommodates a high degree of elongation. So you can elongate it. Is it there yet? And I had a conversation today with someone else in the industry, and we think that certainly we could have a little better elongation of it, but you still can elongate it, but it certainly can do that. When you're looking at your production considerations, I think you got to look at, first of all, the substrates. The metal, if it's a metal, if it's a ceramic, plastic, elastomers, or printed circuit boards. So really, what we have found, these are the coated substrates that we certainly been dealing with in the medical device industry. The coating property, void-free across all surfaces. So that's something I'm sure a medical device person, depending on your application, are really looking at as void-free. Also, coated surfaces, free of all contaminants. That's the last thing we need in this industry is contaminants, so you certainly want to take that into consideration when you're looking at production capabilities. Considerations. So as we talked about the liquid coatings, and then you have the non-liquid coating Parylene, which is done in a vacuum, but there's a number of ways to apply. Number one, selective coating. It leaves areas free of coating. So obviously there's been a big push for selective coating in the marketplace because of the lack of overreach of the spray. You can actually precisely put it down. There's various application methods. You can brush, you can dip, you can spray, you can selective spray, meniscus coating, wave, and vacuum deposition. So really, basically, these are your application methods that you have with high-performance conformal coatings. Application implications. And these are the implications that these are going to have. So you got cost, because let's face it, cost is definitely an implication out there and a driver to what you need to do. The thickness control, how can you control the thickness and how precise can you control the thickness, because that's very, very important. The transfer efficiency, environmental impact. As we all know, the environment is very important. It's becoming more important. So that's certainly something you're going to take a look at, in your application, what you need to do. And also it has a cost impact. Production volumes. What's your volumes? Because volumes are going to have an effect on what you need to go with, and the performance demands. What are the performance? What's the demands of your products and your customers need? That's going to definitely have an effect on your production consideration. Okay, narrowing the choice. Analyzing performance requirements against coating properties. So you really want to take a look at what's the performance of your end product and what's that got to do with the coating properties. So you really have to take a look at what your performance is, and then really take a look at the performance characteristics, the narrowing the choice that we kind of showed you up there, and take a look at, does that fit what I really need? Because all these coatings, each one of them have a niche. In a lot of cases, not one has a niche for every application out there. So they all have different niches and field fit and modifications out there for your application. So dielectric performance requirements, that's going to definitely be one of the performance characteristics that you're going to be looking at. physical isolation, mechanical protection needs, mechanical and shear force vulnerability, biocompatibility, biostability requirements, substrate flex and elongation potential, surface lubricity requirements, moisture, solvent, chemical, fungus exposure. So definitely, that's another narrowing the choice. VOCs and RoHS concerns. You know, as this year, next year, and moving forward, RoHS is going to definitely be a big driving force in this market. Adhesion challenges. You know, what are going to be your adhesion challenges? Because let's face it, if you don't have adhesion to your product, the product's definitely not going to, you know, it's not going to react the way you want or perform the way you want. Sterilization requirements. Obviously, you know, majority of these products need to be sterilized, and we'll be showing you a slide of that later on in the presentation. Coating removal requirements. Certainly, you know, everyone's got a concern that, hey, if I put it down, I got to reject, now how am I going to remove it? That's definitely another choice that you need to look at, and that's going to be determined upon your device and where it's going. I'd like to talk to you about, we talked about Parylene, which is a non-liquid material versus liquid coatings, and wanted to show you here what the difference is between basically a vacuum deposited polymer versus a liquid coating. There's no cure, it's a precise uniformity, and there's no bridging. There's no liquid capillary action or meniscus properties, and you can see the coatings, you know, on a liquid coating, you know, you can see where you're going to be going on the thickness versus the Parylene, so you're going to go with a thinner film. That's going to be a more uniform film. Parylene far exceeds the electrical, mechanical, and barrier properties of liquid coatings per unit thickness, and Parylene withstands ethylene oxide, radiation, and other autoclave sterilizations. Here's the different variants of that material, and you know, it's in a powder form, but you can see the end. That's a non-chlorinated version. You got the chlorination version with the benzene ring, you got dual chlorination of the atoms of the benzene ring, and you got a fluorinated version. So they're basically the four variants of the Parylene. And this is a quick look at the properties. You can see, you know, some of the gas permeabilities, the moisture vapor transmission, the water absorption, the dielectric strengths, the surface resistivity, the dielectric constant, and the dissipation factor. So that just gives you a quick look. You know, a lot of people are looking at this dielectric factor and the water absorption, and also up here the gas permeability in the medical device industry. So those are basically the three variants. Primarily the main variant here is C, and a lot of silicone parts use the N because of the lubricity. Here's the process. You got vaporization, so you can see where that is. It actually sublimes itself at this stage. It's in a powder, it's a white powder. You got the pyrolysis zone, which is into the 650 to 700 degrees C, so you're breaking this down into a monomer. Here's the deposition, where actually it's a gas, and it actually flows itself into the chamber at room temperature. And you have a cold trap here for any excess of film, not film, but any excess of the gas. So it'll go to the cold trap. So this, we just wanted to show you basically how this process is different from a selective spray coating application or a brush on or a dip. So you can see this is how basically a non-liquid coating process such as Parylene operates. I think in the coating side of things, when you're really looking at, do I want to do it in-house, or do I want to bring it, you know, do I want to do it out of house, send it to somebody, or do I want to do it in-house? And that's something we really wanted to talk about here, is basically, there's a couple ways you look at it. In the coating implementation side, if you're looking at outsourcing your coating service, whether it's liquid, whether it's non-liquid, you know, you're definitely going to look at when you're outsourcing it. It eliminates the equipment, raw material, factory floor space, energy, staff, training, and administration costs. The other thing is incoming parts are 100% tested and qualified, and for most cases, no matter who you send this to, from a liquid standpoint or from a non-liquid standpoint, certainly they've got the engineering and the technical expertise, and they do it every day. In-house coating operations basically can be cost-effective option depending on your production volumes and manufacturing resources. And basically what you'll find is most people, if they bring it in-house, they want clean rooms, they want to have it controlled within their environment and control their production within their own facility environment. You'll find that why a lot of people bring it in-house. Trained engineering support for in-house operation are available from qualified sources. So basically most of the people will get trained, okay, they'll get their people trained, and they'll actually bring up their operations themselves. That's something you need to look at in-house versus out-of-house. Also, quality control. That's another important factor when you're looking at high-performance conformal coatings for medical electronics. Conform to rigid standards by means of effective in-process inspection and intensive staff training covering process steps and customer requirements. So basically, when you look at high-performance conformal coatings for your applications, you really need to take a look at the quality. It's just not, you know, like it used to be in the back room somewhere where you've got fumes and all that. It's really treated as an integral part of your process. Because at the end of the day, it's probably one of the last processes you're going to do before your product goes to market. And so in fact, this is an important part of the quality side of this, of your coating process or your high-performance conformal coatings. Again, quality control. Employ precise instrumentation to accurately measure film thickness. And you definitely want to make sure you're hitting your film thicknesses, and you really want to make sure you employ precise measurements. You know, not just like a micrometer, but you really want to get into some of the instrumentation so you're actually controlling your thicknesses from lot to lot. It's very important. Employ visual aids to guide careful visual inspection. A lot of people, they like to just look at the visual side, so please make sure that you employ effective visual aids, whether it's black lights or the proper lighting or the proper microscopes, but it's extremely important that you really provide yourself with visual aids. And then use detailed documentation and process control for repeatability and consistency from part to part. Good travelers, good documentation. You know, how did I run this part? What were my settings? You know, what were my head settings? What were my pressure settings? What were my temperature settings? It's very important that you document that, and frankly speaking, you really should be looking at some type of a traveler. You know, a traveler from lot to lot that documents your key driving forces on what you're doing in your process. Whether it's your material makeup, you know, your lot consistencies, what did I do here? You need something to track back. And there's been a lot of occasions out there where, again, people treat this process as, well, it's the last thing out the door, and I really don't have good traceability. So then things get a little out of whack, and people start looking back and say, gee, you know, how did I do that? How did I do that to get reproducible results? Because let's face it, that's really the key to it all. And is it process, you know, is the process good for your operation? Does it lend the flexibility needed to give you the performance, the flexibility that your customers need or that you need in your operation? That's extremely important. Advantages of Parylene, because we really, you know, talked about the other materials. You know, some of the advantages you're going to see, and I'm not going to go through them all, but you're going to find favorable ratio of production to coating thickness, thermal stability, freedom from cure stresses, so you're not going to see any stresses. You're also going to see true pinhole-free coverage, and also green technology, low VOCs and RoHS compliant, and biocompatibility and biostable. So those are some of the advantages of the non-liquid process of Parylene. To wrap up the presentation, I really appreciate everyone being here today. I'd like to say, when you're looking at high-performance conformal coatings for medical electronics, okay, you really need to be looking at an effective coating material and production plan that depends on a disciplined and informed review of the following. Precise coating performance requirements, all material and process options, governing standards and documentation requirements, and assistance from an experienced and qualified supplier. And that can be a qualified supplier, can be your equipment supplier, your coating material supplier, your actual quality You know, if you have somebody, they have a quality consultant or quality company that comes in, you need to utilize the people that are in the field from your suppliers because they certainly have that information. And if you have any questions or anything, you can go to booth 1791 in Hall D. Thank you. Yes. Yes. ISO 9001, 2008. Also AS 9100. Yes. Mm-hmm.